OK, so I want to begin by reminding you of a little example that you've probably seen something quite similar to this in your first course in linear algebra. And for this, I'm just going to describe a map, a linear transformation. Let's consider the linear transformation that takes this vector. So this you could think of as something like 1, -1, and leaves it fixed. But then takes vectors pointing this direction. Let's not make it quite so long. Pointing in this 1, 1 direction, and doubles the length of them. Right? So there's my linear transformation. So there's some matrix A, some 2 by 2 matrix that should describe this. Well, why is there matrix A? You should verify this really is a linear transformation. But once you believe it really is a linear transformation, then it's like, sure, there should be some matrix that describes this movement. How do we find that matrix? Well, one way is you just ask, what does this linear transformation do to the first elementary basis vector, 1, 0? What does it do to the second elementary basis vector, 0, 1? And you can try to figure that out. But I think the story you learned in your first course in linear algebra, a story you should have learned, is the way we're going to get from here to here is we're going to take a little detour. First, we're going to move up by just rotating these guys. So I'm going to rotate them, 45 degrees counterclockwise. So I'm going to rotate them 45 degrees counterclockwise. And now I'm going to have a vector pointed just in the x direction and a vector pointed just in the y direction. Then I'm going to do the expansion that I want to do. So now I want to double the length of the blue guy. So I'm going to double the length of the blue vector and leave the orange vector at the same length. And then I'm going to rotate it back. And then I'm going to rotate it back. So now I'm rotating it by 45 degrees clockwise. And the series of moves gives you the same result as the single move. And then since any linear transformation is represented by a unique matrix, you can say, what is this matrix? Well, to figure out this matrix, let's just figure out the matrices at each step here. Up here, well, this isn't too hard of a matrix to figure out. The vector, let's just say this is the vector 1, 0, is going to stay at 1, 0. Whereas this vector here, 0, 1, is going to become 0, 2. It doubles, right? 0, 2. How about these matrices? Well, if we just remember how these maps work, so like what does the rotate 45 degrees map do? If it's rotating up, your first vector is going to go to root 2 over 2, root 2 over 2, whereas the second vector goes to minus root 2 over 2, root 2 over 2. Rotation matrices have a nice form. You know what these look like. When you rotate the other direction, when you rotate 45 degrees clockwise, what does that map do? Well, it's a very similar matrix. It's just these guys are going to get moved down. Your x and y are going to just rotate down 45 degrees. And so now you can get still positive root 2 over 2, but the negative root 2 over 2, because the guy who was here is now down. And the guy that was straight up is now in this position, root 2 over 2, root 2 over 2. So what is this matrix A? This matrix A is the same thing as, let's make sure we get the order correct. You first do this matrix, then this matrix, then this matrix. But if you do this matrix first, that means you want it to be rightmost. Since this is the first transformation you do, you want that one to be furthest on the right. Then you do this transformation, 1, 0, 0, 2. And then you do this last transformation, root 2 over 2, minus root 2 over 2, root 2 over 2, root 2 over 2. OK. We happy with that story? Well, I picked this example somewhat strategically, because if we look at this guy to the right, we're like, this isn't just any old matrix. But this matrix in the middle is a very special matrix. It's a diagonal matrix. Right? And what can we say about these guys to the left and to the right? Well, we said this guy on the left is the 45 degrees clockwise matrix, and this guy on the right is the 45 degrees counterclockwise matrix. But another way to think about them is, what is 45 degrees clockwise doing? Well, that's just the map that takes you from up here to down here, right? So this is really just your change of basis map, where you're changing from your standard basis to this other basis. So this here is just change of basis. And here to the right, you just have the inverse of the change of basis. That's the map to go back up. If change of basis is taking you down, it's change of basis in the other direction. So it's your inverse of your change of basis. In general, we have that A equals P D P inverse, where D is diagonal, P is your change of basis. Yeah, there's more you can notice as well. These numbers 1 and 2, what's special about them? What do we call those numbers? These are eigenvalues, right? These are just my eigenvalues. With associated eigenvectors just being the column of this guy. Right, like this first column, root 2 over 2 minus root 2 over 2, is just this guy right here. And notice that stayed the same under the transformation, so it was multiplied by 1. If you call that first column V1, you have that A times V1 is just one copy of V1. So V1 is your first eigenvector with corresponding eigenvalue of 1, because that vector just stayed the same. Things in that direction don't change. Whereas the second column is your V2 with corresponding eigenvalue down here, lambda 2 being 2. So here, A V2 is my second eigenvalue of 2 times V2. Because if you take something in the root 2 over 2, root 2 over 2 direction, this blue guy, what happens to it? Well, it's the same thing, but multiplied by 2. So in particular, we say A is diagonalizable, where the diagonal is your eigenvalues. The P is your change of basis, comprising the eigenvectors, right? Now, can you always do this? Is this always possible? This is called diagonalizing. This is how you diagonalize a matrix. Is this always possible? This was a big part of your discussion thinking of first course linear algebra, probably like the last third of the course, right? When can you diagonalize? Okay, you have a bunch of criteria that end up being equal to each other, right? The one I'm interested in here is that you can actually find eigenvalues. You actually have n eigenvalues, right? If this is an n by n matrix, you actually need to have n eigenvalues. And so this exists if there exist, it's an if and only if actually, n eigenvalues lambda 1 through lambda n. Now, when I say n eigenvalues, I'm just going to note that this is counted with multiplicity. So some of these might be showing up more than once, right? A multiplicity, there's definitely a p in there somewhere, with mult, okay. What do I mean by that? Well, if this had been the map that stretched these both by a factor of 2, the eigenvalue 2 would show up twice, right? So sometimes you might have repeats, but if you count those repeats just as distinct eigenvalues, then you get n. Well, you have n eigenvalues and a corresponding n linearly independent eigenvectors, which are your v1 through vn, and that just gives you what your p is. You can just write p to be the columns being those eigenvectors. Okay, so this is meant to be a bit of a review, kind of reminding you some of the mechanics of how this stuff works. But again, maybe the last thing I'll say is you can always do this if you pick a field where you always have, well, where do eigenvalues come from? Do you remember how to find eigenvalues? So maybe I should just do like a quick aside here. Like eigenvalues are solutions to the guy a times v equals lambda v. So what does a solution to that look like? Well, one way to write this is it's a times v minus lambda times your identity times v is the 0 vector. Pull out your v, a minus lambda I times v is 0. And then this is where the determinant comes in. You're looking for when does this have solutions? Well, this will have non-trivial solutions exactly when the determinant of a minus lambda I is non-zero, right? Oh. You have non-trivial v when my determinant is 0. Thank you. When my determinant is 0. So this is what you call your characteristic polynomial. So I'll just call this like p sub a of lambda. It's a polynomial in lambda. This is just some, you just have some equation that have a bunch of lambdas in it, right? Some matrix of a bunch of numbers and lambdas, and you calculate the determinant. So this is your characteristic polynomial. And so your eigenvalues, lambda, are solutions to when your characteristic polynomial is 0. Roots of the characteristic polynomial. And so like, okay, what's a field that we can pick so that every polynomial has roots? Well, just work over C. If you work over the complex numbers, then by the fundamental theorem of algebra, you're always going to have a root to this. You're going to have n roots counted with multiplicity, right? And so this is always possible. Let me get a new color, green. You can always do this. This is always possible for matrices that are complex, that have complex entries. If you have real entries, you might get into a problem where some of these solutions are complex, and then you'll only be able to write this out if you allow for complex values in D. But if you're working over the complex numbers, you can always factor like this. Okay, so that was like, what, a 10-minute review of several weeks of your first course in linear algebra. But in many ways, this is going to motivate what we want to do for the next several weeks in this course. Because we want to say, okay, if working over the complex numbers, you can always write A as some change of basis P times a diagonal matrix D times the inverse of some change of basis. What if I want to insist upon that basis being a nice basis? For instance, what if I want to insist upon my basis being an orthonormal basis? What if I want to insist that my basis v1 through vn is orthonormal? Well, if your v1 through vn is an orthonormal basis, then P would be what kind of matrix? What do you call a matrix where its columns form an orthonormal basis? Unitary. Great. So we're looking for when you can write A with a unitary basis, and then the inverse of a unitary basis. What's the inverse of a unitary basis? The conjugate transpose. And we want to say, okay, if I insist that this is unitary, and I insist that this is the inverse of unitary, which is the conjugate transpose, then can I still get a diagonal matrix there in the middle? And it's like, well, you're asking for too much, right? Like that's too big of an ask. But it turns out that we can get a matrix in the middle that's upper triangular. So here T is an upper triangular matrix. And U is a unitary matrix. Thus, in particular, U inverse is just U conjugate transpose. So this is called the Schur triangularization. Triangularization. And it just states that you can write A of this form for any complex matrix A. Now, again, if your matrix happens to have real numbers, you get into some trouble, just like before, right? You may not always be able to do this. But if you allow complex numbers, then you will, just like before, how you can always diagonalize, you can always, in fact, insist something more, that these are unitary matrices. They have an orthonormal basis you're working with. But then you lose a little bit of information here where your matrix is not necessarily triangular. It's not necessarily diagonal. It's upper triangular. Although sometimes it's diagonal. Can you think of an example? We just did one. This first example we did, what do you notice about this guy? What do you notice about v1 and v2? This is an orthonormal basis, right? The magnitude of each is 1. And if you dot them together, you get a half minus a half, 0. So in fact, here's an example where you actually have a unitary matrix. You actually have a unitary matrix. And then what's the inverse of this matrix here? Well, notice this is just the conjugate transpose, which is just transpose because it's real numbers. It's just the transpose of this matrix. The minus just moved from the bottom left corner to the upper right, right? So we've actually already seen an example where it's of that special form. And here it actually was diagonal. In general, it's not going to be guaranteed to be diagonal. If you want to insist upon this being unitary, you might have an extra entry up here in the upper right. OK, so that was a really good motivating example for us. So what I want to do today is I want to prove this. And then once we prove it, I'm going to use this fact to show some nice properties of matrices that fall out of it. Right? Since unitary matrices are really nice, you understand a lot of things about them. Once we have this as a fact, we'll be able to rewrite matrices and recover lots of facts about matrices. Facts that you already know, but maybe you haven't seen justified so well. So here we go. Let's try and prove this. And I don't know if it should be at all obvious how to do this proof. Right? Like I look at proofs like this, and you usually want to think like, oh, how could I have come up with this proof, right? If I was trying to prove it from scratch. And I don't know if you have too many clues in the problem. And so sometimes when you don't have too many clues, you just cheat. And by cheating, I mean use induction. So we're going to use induction. Now, in some sense, induction is cheating because it seems like proofs by induction just give you an answer, you don't really understand why. But actually, we're going to see a recursive way of thinking about these problems, which in practice is actually how you find this unitary matrix in the upper triangular matrix. You just kind of follow the process we give in the proof, and that essentially is your method for recovering the unitary matrix and then the corresponding upper triangular matrix. So this is actually quite a good proof. So we're going to use induction. It's going to be induction on n. The n is the size of our matrix, right? So let's think about the case n equals 1, our base case. Is that true? So I have a 1 by 1 matrix. Maybe it looks something like a single value A. Can I write it of this form? Well, you might be like, what is an upper triangular matrix when you just have one entry? It's just one entry, right? Like if it was like 2 by 2, it'd be the bottom left, but there's nothing to be 0 in a one entry. So you can just make A your upper triangular matrix. And then what should be your unitary matrix that goes to the left? Just make it 1, right? So there you go. There's the conjugate transpose. So trivial. There's nothing to show in the case n equals 1. OK. So now let's assume that this statement is true for n minus 1 by n minus 1 matrices. Of course, matrices of complex values. And I'm going to say we're given, consider an n by n matrix that I'm going to call A. OK. The goal is going to be start trying to pick away at A until we're just left with an m by 1 matrix to which we can apply the inductive hypothesis. So how are we going to do this? Well, we kind of understood how we did it here with diagonalizing matrices. We're going to try something similar. I'm going to begin by looking for an eigenvalue. It's going to turn out at the end of the day that this triangular matrix will have on its diagonal all of your eigenvalues anyway. We'll be able to verify that in a moment. But we're going to consider an n by n matrix A, and let's just find some eigenvalue of it. So A has some characteristic polynomial. Of the form, characteristic polynomial of A with some variable lambda. And since we're working over complex numbers, that guy has n roots. But in particular, we can find one of the roots. With a root, so that root is lambda 1, I'll call it. So that's your first root. That's an eigenvalue. And hence there's going to be some corresponding eigenvector v1. And eigenvector v1. Now your eigenvector is just a direction, and you're saying in that direction, things get scaled by lambda 1. But instead of picking v1, I could also have as my eigenvector like 2 times v1. Right? If v1 is an eigenvector, so it's 2 times v1, because 2 times v1 times your matrix would be 2 times v1 times lambda 1, so it's still an eigenvector. You can scale an eigenvector, and it's still an eigenvector. And so without loss of generality, without loss of generality, we may assume that v1 is a unit vector. The magnitude of v1 is 1. If it's not, just scale it to make it 1. Just pick an eigenvector that has length 1, right? That's all I'm saying. Now, once I have a single vector, from that vector, I can use some process like Gram-Schmidt to extend it to get an entire orthonormal basis for whatever my space is. Here I guess I'm working in the complex numbers. So I have like Cn I'm working in. But I may extend to an orthonormal basis v1, so I keep v1 the same, but then I find some v2, some v3, all the way up to some vn. Yeah, I've given you one vector. You can find a collection of n minus 1 other vectors so that the entire collection is orthonormal. What I want us to do is I want to define the matrix big V to be the matrix that has as its columns v1, v2, all the way through vn. But it's going to become a bit of a pain for me to keep writing out v2 all the way through vn. And for simplicity, I'm just going to write this as the first column is the column v1, and the rest of this is some matrix that I'm going to call big V2. Now, let's remember what kind of matrix big V2 is. It only has n minus 1 columns, but it still has n rows. So it's an n by n minus 1 matrix right there, V2. We happy with that definition? We understand what I'm saying there? OK. Let's take a moment now and consider what happens if I multiply A by this V. So I'm going to think about, well, so what's our goal? Like, let's remember our goal. Maybe I should write it up here. My goal is I want to write A as some unitary matrix U times T times some unitary matrix U conjugate transpose. But that's the same thing as I can bring this on the right over as its inverse. So it comes over as U on the right. And I'll bring U over on the left as its inverse, U conjugate transpose. That's the same thing as saying this, right? I just want us to check really fast. Have we found the matrix U already? Is V going to be our U? Let's just check. Does V star A V give us out the triangular matrix we want? Because if we can show this is triangular, we're done. Now it's going to turn out it's not triangular, but it's going to be a step in the right direction. So let's see what this matrix is. OK, V star is just the conjugate transpose of this guy. So taking the transpose means I'm switching rows of columns. So now V1 is the first row, and this V2 guy becomes all of the matrix below him. He went from being an n by n minus 1 to the transpose of that, but it's the conjugate transpose. So it's taking the conjugate transpose of those. Still have A right here in the middle. And then I have V to the right, which is just a V1 with a V2. Well, now you want to take a second to convince yourself how matrix multiplication works. But since we're just doing row by column, row by column, row by column, row by column, this first column is just going to become AV1. And then you'll continue that with all these other columns, which will give you A times whatever this V2 is. So like, convince yourself that's true. And I still have this matrix to the left, which has a v1 star on top, the conjugate transpose of the vector v1, and the conjugate transpose of the submatrix v2. And again, just doing row times column matrix multiplication, where you get this first row times this first column will give us v1 star a v1. That row times all of these columns will come out to be v1 star a v2. This bottom guy is a matrix times this other matrix down here. I mean, doing row and columns, just times the matrices together. So down here, I now have v2 star a v1, and then I have v2 star a v2. So if you're not familiar with this kind of way of working matrices, just really convince yourself that once you've broken a matrix up to these submatrices, you can just multiply the corresponding. As long as the dimensions are right and to make sure that they all work out, you can just multiply them out in this way. So these correspond to submatrices, or these are matrices. This here is a particular number. This is a number, because this is a v is a vector, but this is like a matrix, right? This is a row, this is a column. Okay. Well, let's think about these values a little bit. What is A times V1? We said V1 is an eigenvector with corresponding eigenvalue lambda 1. So A times V1 is just lambda 1 V1. This would just be a copy of lambda 1 times your V1. But you can then pull that constant out, and so you have lambda 1 of v1 star times v1, and we picked v1 to be a unit vector, so v1 star times v1 is just 1, so this just gives you lambda 1. Okay, any other places where we can do some tricks like this? Well, let's think down here. A v1 is again just lambda 1 v1. I can pull the lambda 1 out, so this is lambda 1 times v2 conjugate transpose times v1. But now think carefully about what this is. What is v2 conjugate transpose? I mean, maybe I should write it out one more time to remind us. v2 is just the guy comprising vectors v2 down through vn. And taking all of the conjugate transpose times the vector v1. And times that by lambda 1. So I'm going to do this row times that column, the next row times the column, next row times the column, and so forth. But what is like v2 conjugate transpose times v1? Zero. Why? I constructed my basis to be orthonormal. So in particular, any vi conjugate transpose vj, or vj conjugate transpose vi, will be 0 for I and j distinct. If they're equal, it's 1. Otherwise, they're 0. And so this just gives you a 0 vector times lambda 1. So this down here is just the 0 vector. This in the bottom corner is just the 0 vector. So maybe I'll just write that. That's just the 0 vector. How about up here? Exact same story, right? Okay, well, I guess it's not exactly the same. No, because it's on the wrong side. Okay, we'll leave him. Not going to touch that guy. Respecting him. How about down here, though? What can we do with this guy? Well, what size of matrix is this? What do we say that V2 is? An n by n minus 1. This is an n by n minus 1. And how big is A? A is an n by n. So this guy and this guy. And the conjugate transpose, since we're transposing, it's going to flip that. So that's an n minus 1 by n. So when I solve this out in the bottom corner, it comes out to be a n minus 1 by n minus 1. Right? So, let me free up a little bit of space here. we now have a matrix that looks like, up here, it came out to just be a constant number, lambda 1. Down here, it came out to be the 0 vector. The rest of this column is just zeros all the way down. Up on the right, it's some ugly thing, v1 conjugate transpose a v2. But down here, it's an n minus 1 by n minus 1 matrix. Hence, by our inductive step, that n minus 1 by n minus 1 matrix can be written like it's this form. This can be written some unitary matrix times T times the conjugate transpose of that unitary matrix. But to avoid confusion with the goal of what I'm trying to reach, I'm just going to call this U2, U2, and T2. So that's me using the inductive hypothesis right there. And then it's like, what is this matrix? Well, it's not quite upper triangular, because you have an upper triangular matrix T in the middle here. If it was just lambda 1 with zeros all the way down and that T, now it's upper triangular. It doesn't matter what mess you have up here. You can have whatever mess you want up here. You can have all this mess up here. And this is V2, a matrix. That would be upper triangular, because T is upper triangular. But in fact, that's exactly what I have. If I just pick here the matrix that's U2, 0, lambda 1, and, oh no, there should be a 1, and 0, I think that does it. And here I'll pick the matrix 1, 0, 0, U2 conjugate transpose. Okay, let's take a second to think about this. When I do matrix multiplication, row times column, that gives me lambda 1. Row times column, he stays the same. Row times column, he stays the same. Row times column, I pick up the U star right there. Multiply it out, I recover the matrix above. So yeah, that's correct. And this is a matrix where, I'll just use the yellow, this guy here we just said is upper triangular. Upper triangular. This first guy, well, U was unitary, and then you just take a 1 here. Zeros everywhere else, still unitary. Still unitary. Right, 1 dotted with itself is 1. This column dotted with any other column will be 0, because you have zeros everywhere else. This is a 0 vector, right? These are all zeros all the way down. Zeros all the way across. And this is the conjugate transpose of the unitary matrix. So this is your matrix U. This is your matrix T. This is your U star. So that completes the proof. Okay. Spent some time on it, but I think it's worth seeing how these induction proofs can play out with matrices. In the last 5 minutes, I just want to note a bunch of really quick corollaries of this. Once you believe that given any complex matrix, you can write it of this form, we have a bunch of consequences. So let me just write some corollaries. Corollaries, we're going to have a bunch of them. This is going to be for any matrix A with complex entries. First, I claim the determinant of A is just the product of lambda 1, lambda 2 through lambda n with these eigenvalues. Well, let's go back and think a little bit. When I was making my matrix T, in the process of constructing it, I got a lambda 1 up here, right? But because this is induction, because this is recursive, you have the same thing has to be true for this upper triangular matrix, and it goes all the way down then. It just follows. Like if this is lambda 1, that's going to be lambda 2, then lambda 3, and lambda 4. So this upper triangular matrix T must be of the form where the diagonal of your upper triangular matrix is just your eigenvalue. So the diagonal of t, so it's not just upper triangular, it's an upper triangular where you have along the diagonal lambda 1 all the way through lambda n, zeros down here, and then whatever you want up there. And therefore, why is this true? Well, it's true because the determinant of A will just be the determinant of a unitary matrix times t times the conjugate transpose of a unitary matrix. But that's just equal to the determinant of u times the determinant of t times the determinant of a unitary matrix. This is plus or minus, well, this has absolute value 1, but when you multiply it by its conjugate transpose, those will cancel, giving you just 1, giving you the determinant of t, and then since the diagonal of the determinant of t is your eigenvalues, you recover, this is just your eigenvalues. So this comes immediately from this triangularization. Similarly, you get that the trace of a matrix is just the sum of its eigenvalues. So why is that true? Well, again, you just take A, you find this triangularization, so that's just going to be the trace of u times A times u conjugate transpose. Then, I'm going to use a property of trace that you may not remember, but if you have the trace of some matrix like X times some matrix Y, you can commute those matrices inside. Now that's not to say the trace of X times the trace of xy is the same as the trace of X times the trace of Y. That's not necessarily true, but you can commute things within the trace. This is the same as the trace of U transpose UA. Actually, we proved this a couple weeks ago. When we were talking about inner products, I gave the example of how a trace can be an inner product. And that's only true if it's commutative, right? So that comes from the fact, I mean, we showed it when we showed that the trace was an inner product. So if you remember, you believe the trace is an inner product, then you believe you can commute things inside. But U conjugate transpose times U is just the identity matrix, so that's just the trace of A. Sorry, that shouldn't be A, that should be T. That should be my triangular matrix. That's just the trace of your triangular matrix. Yeah, okay, so that follows very quickly. And let me do one last one, perhaps the most important. Consequence of the Schur triangularization, and that's Kaylee Hamilton. Which just states that if P sub A lambda is the characteristic polynomial for A, then you can actually plug the matrix A in and get out the zero matrix. Because I'll try this big zero. It's all zeros. Okay. We won't have time to do the proof of this, but the proof is actually quite identical. It's quite similar. It's a little more complicated than the previous ones, but you began by triangulating. So the idea of the proof is begin by taking this guy A and use your triangularization to say that's some UT U star, but then that's just going to give you, well, there's a bit of an argument involved here, but argue that if you think about what this looks like, you can show it's of this form, and then you just have to show that this comes out to be 0. Which you can do, it's a little bit tricky, it's a proof by induction for the last step. But it uses the same triangularization. But I mean, this is quite nice, right? So maybe I'll pick up next class, and I'll give you some consequences of Kaylee Hamilton, and why Kaylee Hamilton can help us calculate things like the inverse of a matrix very quickly, and things like that. But let's stop there for now.